Hello, I am here to talk about our work, data curation in the Internet of Things, a decision model approach. The work has been developed by the following authors: Francisco José de Haro-Olmo, Álvaro Valencia Parra, Ángel Jesús Varela Vaca, and José Antonio Álvarez Bermejo, from the University of Almería and Sevilla. The structure of this work is the following: an introduction, and next section we talk about the use case, a real set data set. The next section, our proposal and an evaluation, and finally we talk about the conclusion. First, the introduction about IoT quality usage. So, Internet of Things is more realistic than ever. It is common to find hundreds and thousands of devices connected to the Internet and to each other in different contexts. Nowadays, IoT is used as a service in big data pipeline as a mechanism to integrate large amounts of data-centric services. As a consequence, the data generated by sensors in IoT context can easily reach the dimension of big data. In this respect, IoT must tackle multiple challenges in a pipeline of big data concerning the activity related to data acquisition of data curation. Nevertheless, the use of poor quality data can produce terrible consequences: incorrect decision making, damaging the performance in the operation, increasing costs. Therefore, to use enriched data with an expected desired level of usability has become crucial to achieving success. In general, the integration of the IoT with big data is carried out in the data acquisition activity in the context of big data pipeline. Thus, the IoT requires the integration of numerous devices through network. An example is the application of IoT in the context of the agri-food sector by transforming farms into smart farms. Therefore, on the hand, we need to aggregate the heterogeneous data provided for sensors, but ensuring the data quality. And on the other hand, sensors can be affected by external or internal problems by compromising the quality of the data produced. Missing value due to power interruption. Thereby, we need to evaluate the quality of the data in the process of data curation in order to avoid poor quality data in afterward tasks. In this regard, there are two main challenges the data curation for IoT integrated into big data context. Define an IoT big data pipeline architecture that enable the data acquisition and data curation in device connected context, and include in the pipeline an approach to measure and evaluate the data quality in the data produced by sensor. Hence, a proposal is the M4DQ, which is a methodology that enables the automatic generation of recommendations on the potential usability of data in terms of its level of data quality. We have a case of use, and we have a data set of just over 1 million records. This information processed from agricultural farm, and the dataset gathers information of sensors distributed in an agricultural farm. Sensors provide measurement hourly and daily of volumetric water content, soil temperature, and bulk electrical conductivity, collected at 42 monitoring locations and 5 depths across the farm. The information is saved plain text file separated by sensor, day and hour. Each record contains the following fields: location, date, time, humidity, temperature at different depths. In our study, we propose to use our approach for IoT big data pipeline if a real case study. First, we propose to choose a case study based on the real dataset. The dataset includes data straight from several sensors in an agricultural farm. Subsequently, we want to apply DMN for the dataset to evaluate the usability of the data in terms of the data quality, to discard those that don't provide sufficient information and include in the final catalog the dataset that have obtained an adequate evaluation according to the data quality requirement. Carry out by means of the defined decision rule. To do this, we have to define the decision model to be used. The decision model for the case study is the next. The decision model is focused on two quality dimensions, completeness and accuracy. Thus, incompleteness and inaccuracy of the data could cause confusion, leading to incorrect or unrealistic value being entered into the system and leading to appropriate decision made when further processing data collected. The objective is to evaluate the completeness and accuracy. In this respect, we have grouped the data validation on each of the business rules, BR1 to BR13, into two quality dimensions, completeness and accuracy. Missing some relevant data from the dataset may lead to undesirable result. In this case, we define business rule BR1 to BR8. The first three rules are in charge of ensuring that the location, data, and time contain data other than null, empty, or blank. Thereby, for these three rules, the returned result will be false if the that field is null, empty, or blank, and true otherwise. In the next case, in the case of BR4 to BR8 rule refer to the sensor on the different depths, taking the depth sensor and the sampler read the humidity and temperature. The BR4 rule take humidity and temperature as inputs, so that when the inputs are null, the result will be 0. If either of the two values is other than null or contain the empty file or the string NA, the result will be 1. In any other case, the result value will be 2, which indicate that it contains data that can be accepted. In the list of rules which are numbered at this level of business rule, the first one that meets the imposed condition. In other dimension, we have accuracy. In this case, we are interested in detecting those cases in which the value collected by the sensor are not reliable due to the extreme value. BR9 to BR13 rules deal with this case for sensors located at different depths. For instance, the BR9 given takes an input value, the humidity and temperature data, in such a way that 1. If the humidity is the range of 0.15 to 0.7 and the temperature between 1 and 45 degrees, the result will be realistic. The next case, where the temperature is below 1 degree or above 45, it will take as a result unusual. In the case where the humidity is above 0.7, it will also give a result unusual. In any other case not covered, the result will be unrealistic. It is important to say that the result obtained from the data validation of the business rules, BR1 to BR13, will be delivered to the high level where the data quality measurement is performed. So, the result of the completeness dimension measurement depends on the output value from BR1 to BR8 rule. Each line of the decision table will be triggered into context to the field BR1, 2, and 3, plus a value greater than or equal to 2. For the value coming from the validation of the data of the reading of each of the depth sensor, BR4 to BR8, in this way we will know how two readings are considered complete. These rules are evaluated following the HIT policy. We return the number of conditions that are met as given. In relation to the measurement of the accuracy dimension, the following conditions are defined given the input BR9 to BR13. A value of 20 is assigned as a result to each entry containing the string realistic, so that the HIT policy C+ sum up the output value of each condition line that is fulfilled. The result gives a readable accuracy in terms of percentage, with the value 100 being the fact of having a valid reading in all the sensors coming from a register as given. For the data quality assessment, we have defined a decision table. So the possible output of the data quality assessment are set as follows. Suitable for those records that have a completeness measure greater than or equal to 5 and accuracy greater than or equal to 100. It means that the record contains complete and accurate data from all sensors. And next, enough quality when there is at least a value equal or greater than 3 in the completeness dimension and greater than or equal to 60 in the accuracy dimension. It means that 3 or 4 sensors have provided complete and accuracy reading. Bad quality result is given by complete reading from 1 or 2 sensors or with a precision below 60%, and non-usable in any other case. In the decision table, the HIT policy first are applied. Thus, the first entry that match is returned, disregarding the rest. In this final step, the quality level of the data is decided. In consequence, we can decide to include or not the data record in the final catalog. So the decision table, in our case, we have defined as usable data those that have reported a result of the data quality assessment value of suitable or enough quality. returning a result value of use. The rest are the characters of not exceeding the preset minimum, labeled as don't use. The decision model enables us to powerful decision maker based on usability by means of measuring and assessing the data quality of every record in the dataset of new one generated in the case study. In this section about evaluation of the reading processes, we have obtained that almost half are validated as usable. Our proposals allow discard poor quality data, having good quality data, storage optimization, data sensor anomalies, and improving decision making. And finally, in conclusion, we can say that has been implemented IoT big data pipeline architecture, enable data acquisition and data curation in any IoT context. We have used the DMR for the Q approach to measure and assess the quality of the data. We have taken a real dataset from an agricultural sensor. We have defined the decision model, GMN. The process of measuring and assessing data quality has been automated. The usability of data collected by IoT sensor has been obtained. Thank you for your attention. I am here for ask your question. Thank you.